बिस्मिल्लाहिर्रहमानिर्रहीम रब्बिश्रह ली सदरी वयस्सिर ली अमरी वाहलुल उक़्दतम मिन लिसानी यफ़क़हू क़ौली. Assalamu alaikum. Today we will continue section 2.3 analysis model particle under constant velocity, and we will also cover example 2.4 modeling a runner as a particle from the book Physics for Scientists and Engineers with Modern Physics by Serway and Jewett, 10th edition. In the opening storyline, the particle under constant velocity model was represented by the path of motion taking place at fixed speed. You found in the storyline that the time interval between the poles were always the same in this case. Is this result consistent with equation 2.7? Example 2.4 below shows a numerical application of the particle under constant velocity model. Revising the storyline, you are a passenger in the car being driven by a friend down a straight road. You notice that the telephone poles, street light poles, or electric power poles on the same side are located at equal distance from each other. You pull out your smartphone and use your stopwatch to measure the time interval required for you to pass between adjacent pair of poles. When your friend tells you that the car is moving at fixed speed, you notice that all these time intervals are the same. Example 2.4 Modeling a runner as a particle. A kinesiologist is studying biometrics of human body. Kinesiology is the study of the movement of human body. Notice the connection to the word kinematics. She determines the velocity of an experimental subject while he runs along a straight line at a constant rate. The kinesiologist starts the stopwatch at the moment the runner passes a given point and stopped it after the runner has passed another point 20 meters away. The time interval indicated on the stopwatch is 4 seconds. Part A. What is the runner's velocity? Solution. We model the moving runner as a particle because the size of the runner and the movement of the arms and legs are unnecessary detail. Because the problem states that the subject run at a constant rate, we can model him as a particle under constant velocity. Having identified the model, we can use equation 2.6 to find the constant velocity of the runner. Vx is equal to delta x over delta t, which is equal to xf minus xi divided by delta t. Xf is equal to 20 meters, xi is equal to 0 meter, delta t is equal to 4 seconds, giving us Vx of 5 meters per second. Part B. If the runner continues his motion after the stopwatch is stopped, what is his position after 10 seconds have passed? Solution. Use equation 2.7 and find the velocity found in part A to find the position of the particle at time t is equal to 10 seconds. Xf is the final displacement that we need to find. Xi is equal to 0. Vx we found in the last part A, 5 meter per second. Time we are considering is 10 seconds in this question. Therefore, a final displacement is equal to 0 plus 5 meter per second times 10 seconds, giving us the final displacement of 50 meters. Is the result for part A a reasonable speed for a human? How does it compare to a world record speed in 100 meter and 200 meter sprints? Notice that the value in part B is more than twice that of 20 meter position at which the stopwatch was stopped. Is this value consistent with time of 10 seconds being more than twice the time of 4 seconds? To summarize, the runner covered 20 meters in 4 seconds and 50 meters in 10 seconds. The mathematical manipulation for a particle under constant velocity stems from equation 2.6 and its descendant equation 2.7. Equation 2.6 was Vx is equal to delta x over delta t, and equation 2.7 was xf is equal to xi plus vxt for constant Vx. These equations can be used to solve for any variable in the equation that happens to be unknown if other variables are known. For example, in part B of example 2.4, we find the position when the velocity and the time are known. Similarly, if we know the velocity and the final position, we could use equation 2.7 to find the time at which the runner is at this position. A particle under constant velocity moves with a constant speed along a straight line. Now consider a particle moving with a constant speed through a distance d along a curved path. As we will see in section 2.5 below, a change in the direction of the motion of the particle signifies a change in the velocity of the particle even though its speed is constant. There is a change in the speed vector. Therefore, a particle moving along a curved path is not represented by a particle under constant velocity model. However, it can be represented with a model of a particle under constant speed. The primary equation for this model in equation 2.3 with average speed Vx average replaced by the constant speed V. Equation 2.8 says V is equal to dA over delta t. V is equal to constant speed, d is the distance and delta t is the time interval. If a particle is moving in straight line at constant speed, then it is also moving at a constant velocity. However, if the particle is moving in a curved path at constant speed, then it is not moving at constant velocity, it is only moving at constant speed. The velocity vector, it keeps on changing in a curved path. As an example, imagine a particle moving at constant speed in a circular path. If the speed is 5 meters per second and the radius of the path is 10 meters, we can calculate time interval required to complete one trip around the circle. V is equal to d over delta t. This gives delta t is equal to d over v. D is equal to 2 pi r as it is moving in a circle. Therefore, it is equal to 2 pi into 10 meter per second divided by the velocity, which is 5 meter per second, giving us the time of 12.6 seconds. Analysis model, particle under constant velocity. Imagine a moving object that can be modeled as a particle. If it moves at a constant speed through a displacement delta x in a straight line in the time interval delta t, its constant velocity is Vx is equal to delta x over delta t. The position of the particle as a function of a time is given by xf is equal to xi plus vxt. Example, a meteoroid traveling through gravity-free space, a car traveling at constant speed on a straight highway, a runner traveling at a constant speed on a perfectly straight path, an object moving at terminal velocity through a viscous medium. Analysis model, particle under constant speed. Imagine a moving object that can be modeled as a particle. If it moves at a constant speed through a distance d along a straight line or a curved path in the time interval delta t, its constant speed is v is equal to d over delta t. Examples, a planet traveling around a perfectly circular orbit, a car traveling at a constant speed on a curved racetrack, a runner traveling at constant speed on a curved path, a charged particle moving through a uniform magnetic field. May Allah bless us all. Thank you for watching. Allah Hafiz.